last time we have defined homology for Lie algebras. Let's G is a Lie algebra over field K. Then we can consider G modules, left G modules, for example. It's the same thing as left module over universal enveloping algebra. Universal enveloping algebra. Which is just tensor algebra over G modular relation. That associative commutator is the same thing as Lie commutator. Yes, maybe it's we can notice that as for group modulus over group rings, for group ring we have isomorphism of group ring, and the opposite of group ring is the same abelian group with the multiplication in the opposite direction. Opposite multiplication is just a multiplication in opposite direction. And these two rings, in general, for arbitrary ring, are is not isomorphic to the opposite ring, maybe, if it's not commutative. This is not commutative, but in general they are isomorphic because we have isomorphism which sends G to G inverse. And because of this, left R modules is the same thing as, in general, as right, or maybe right R modules is the same thing as the left modulus of the over opposite ring. And so in this situation we have the natural bijection between left and right G modules. And so if we consider G modules, it's not the essential difference between them. And the same thing is true for universal enveloping algebra, because we have isomorphism of UG and UG opposite, which induced by map on G, which sends x to minus x in G. And one can check that if you have left G module, then it has right G module structure, the same thing as right G module, just with the multiplication. It's minus x multiplied by from the left. Multiplication from the right is the multiplication by the additively opposite from the left. And so again, there is no difference essential between left and right models models over Lie algebra. Okay, and we have defined homologies for any G module. We have defined homologies of G with coefficients in M. It's just X over universal enveloping algebra between K trivial module with zero action of G and M, and homology. It's just Tor between K and M. For example, Lie algebra G itself is always module over itself. G is a G module with a so-called adjoint action. Just action by commutator. And so for example, we have homology and homology in coefficients in G itself. It's not trivial. It's so-called adjoint homology and homology. For groups, we maybe have homologies. We can consider homologies and homologies in the group ring with coefficients in the group ring. Homologies in the coefficients in the group ring, of course, trivial because this ring is free over itself, so it's zero. But homology is not trivial also. homology in this thing is not trivial. From topological point of view, they relate with homology of the contractible space with free G action, with compact fibers, with compact supports through the fibers of this cover. Compact through the fibers. So it's more or less the same thing. So it's not trivial in general because of course it's contractible, but no, in general it's not compact. So compact homology, it's not trivial, even for because it's not properly contractible. So it's not trivial thing. No, for homology and for Lie algebra, it's also have some non-trivial homology. Okay. Now here we have, of course, some similar story as for groups. For example, if G is free, Lie algebra, G is free, Lie algebra with some set of generators, then so in general we need to compute homologies. We need construct some projective of free resolution of trivial module K of a universal enveloping algebra, and it always starts from this. We have general augmentation which sends x from G to 0 and unit to unit. It has a kernel. Its kernel is by definition augmentation ideal. From this we obtain that from long exact sequence in homology and homology, we obtain that, for example, homology, that homology of G with coefficient m isomorphic to Tor between EG and M for E greater than 1, and we have, because this is free module, and we have with this one, yes. And we have the end of the long sequence of the following form. We have homology of G and M. Yes. What the long sequence in Tor? I apply Tor with M. I obtain 0, then Tor EG M. No, it goes to 0, yes, and it's second homology, yes, sorry. And what here we have? Yes, we have first homology, then Tor 0, then it's standard product G with M over G. So over G is the same thing over universal enveloping algebra. It's for simplicity. And then we have standard product with UG itself is M, and then standard product with trivial module is the same thing as coinvariance. Oh yeah, I did not say, of course, 0 homology is standard product with K, it's coinvariance. It's M modulo action of G. And cohomology is just home from trivial module to M over G. It's the same thing as invariance. It's just fixed points of action. It's a linearization of group case. In general, it's the general fact that Lie algebra is algebra theory is kind of generalization of linearization of group case of group theory, and so in homology it's also true, and in some aspects it's easier to calculate. It's easier to calculate because it's kind of linearization of group case calculations. We will see this in resolution, in standard resolution, for example. Okay, so we have this exact sequence. So homology, first homology is just kernel of this map. And what is this map? Now, for example, in general we have only just this kernel, but for example, if M is trivial, trivial G model, so action is 0. So coinvariance coincides with M itself, and so this is isomorphism. If it's trivial, then it's isomorphism. And so we have isomorphism here. We have isomorphism here. So in this case, first homology, it's standard product of M with augmentation ideal. Well, because M is trivial, it's the same thing as coinvariance of augmentation ideal itself in standard product with K. No, okay, we can say that it's M over K with K over G with IG, and then I can say that this is the same thing as the standard with vector space with K over G with EG. This thing is just coinvariance of EG itself, and coinvariance is the same thing as M modular action of augmentation ideal from this formula. And so this is augmentation ideal modular augmentation ideal squared. No, exactly as for groups. And so, yes, and tensor with M. So, and as for groups, one can easily check that this quotient, augmentation ideal modular augmentation ideal squared, isomorphic to abelianization of the algebra. Now, for example, in one direction, map just sends x to x. One can check that commutators goes to I squared, because of the relation in universal invariant algebra. This thing goes to the same thing, but this thing is just commutator in invariant algebra, and this thing lies in I squared. So it's correctly defined map, and one can check that one can construct inverse for this map and check that it's isomorphic. But we will see this fact from standard resolution at the moment. No, but the result is that first homology is just abelianization of B of G, no tensor with M. If M is K, then it's just abelianization. Cohomology similarly is just hom is dual vector space, JIB, dual vector space, hom from JIB to K, or to M if M is other trivial, is for trivial models only, of course. Okay, this is the same story, and also, for example, if G is free Lie algebra, if G is free Lie algebra, if G is free Lie algebra on some generators, then one can check this exercise that augmentation ideal is free. Okay. Universal invariant algebra in this situation is just tensor. It's free associative algebra on the same set of generators, and augmentation ideal is just free. No, it's generated. It's ideal generated by X alpha, but in this situation it's free UG module generated with this basis. It's free UG module with basis corresponds to letters, to generators. It's free. And so we have short free resolution of K. So we obtain that all higher homology more than greater than 1 of free Lie algebra in any module is 0. No, as for groups. As for groups. And the same argument, more or less. Okay. And also, similarly as for groups, we have spectral sequence. If we have short-cycle sequence of Lie algebras, we have H, it's some ideal in Lie algebra G, and so we have quotient Lie algebra. H is ideal Lie algebra. Then we have homological and homological spectral sequences. We have homological spectral sequences. And homological spectral sequences. It's Lindon-Hochschild spectral sequences. Now this is the proof is the same as for groups. It's just consequences of base change spectral sequences. Because again we have two base changes for universal enveloped algebras. This base change and this base change. And for this base change, for example, this algebra, if we consider this as module over this algebra, it's free module. It's free UH module with basis is monomials where E alpha is basis of quotient. It's consequences of Poincare-Bergov-Witt theorem. Poincare-Bergov-Witt theorem says that Poincare-Bergov-Witt theorem says that if we have any basis of G, ordered basis, then ordered monomials form the basis of universal enveloped algebra. So if we choose firstly basis of H and then add some basis vectors of quotient to obtain basis of G, we have seen that monomials with H is the basis of UH and monomials of GH is basis of UG over UH. Because any element of UG we have the form of monomial in H and monomial in quotient. And this is element of UH, and so we have that this monomial is basis of UH model UG. And because of this, from this base change spectral sequence, we have some degeneration and we obtain this thing. Here we only need to understand what the action of quotient on homology of H, or homology of H, what the action. We have some action from base change spectral sequence. And in fact, we will understand this action at the moment from standard resolution, because in group case we have understood this action from bar resolution action. From some explicit calculations with bar resolutions, we obtained that this was a joint action. Here with the same thing, but we will also understand this from explicit calculations with some standard resolution, not bar resolution, but Kazoo resolution. Okay, and from this again we have, because it's first quadrant spectral sequences, we obtain 5-term exact sequences in general of the following form. For homology, the following thing, M, H, here goes to coinvariance of action on this homology, then goes to homology of G, and then goes to homology of this coefficient in MH. Yes, and here also in MH. This coefficients in coinvariance, because quotient acts on coinvariance. It may be it doesn't act on M itself, because M is just G model, but quotient acts on coinvariance. No, because here we know quotient acts on coinvariance, no, by action of any pre-image, and because of this coinvariance, change of representative does not change this action. So we have this GH modulus, and we have this homologous. No, and homologous also. For homologies, we have opposite direction. Starts with 0. Now it also acts on invariance. G action quotient also acts on invariance by the same rule. So it acts on invariance and no, it's in general it acts on homologies and cohomologies. Invariance and coinvariance is just 0 homology and cohomology. G M. Here we have H M. M is also H model, of course, but here we have invariance of action on of quotient, second homology in invariance, and second homology in M. In particular, if M is K, is trivial K, for example, then we obtain, for example, from the first, we obtain that, yes, if M is K and G is free Lie algebra. If G is freely algebra, then as for groups, any subalgebra of freely algebra is also free. It's not obvious. Also for groups is not very obvious. For groups, for example, it's Nielsen-Schreier theorem. For groups, it can be obtained from topology, from covering space theory. But for the algebras, is some theorem. It's also some theorem that Lie subalgebra of algebra is also free. It's also free. So in this situation, no, in fact, I think maybe it's not important, but it's also true. This means that in fact we have free resolution of quotient algebra. And again, for any Lie algebra, we can consider surjection from free algebra, and its kernel will be also free. So we obtain this situation where G and H are free. And in this situation, we have that second homology of free algebra is 0 because of the previous thing. So we have, as for groups, we have second homology of GH. No, for trivial model, coinvariance is just model itself. Then goes to this a little bit mysterious coinvariance of the first homology of H. No, it's just abelianization. We know what is this. It's abelianization of, it's the first homology of H. But we have coinvariance of the action of the quotient. Then it goes to abelianization of this free algebra. It goes to also abelianization of GH. So again, this second homology is just a kernel of this map, and we need to understand what this coinvariance. I claim that the action of a quotient on this abelianization is the first homology. It's just, again, it's just a joint action. We consider any class of quotient, consider any representative from G, consider Y from abelianization, and just action just by commutator, xy. I claim that this is this action, And if this is true, then this map, then what is coinvariance of this section? Coinvariance of this section, this is the same argument as for group, but now it's just more easy because it's linearized. What's the coinvariance? Coinvariance, we have abelianization and action by commutator. So coinvariance is just quotient by G acts on H. We have abelianization is H modulo HH, and then it's abelianization. And coinvariance, we just add G here. We also quotes by commutators with elements with G. So this is just this element. This is coinvariance, so it's this thing. This is abelianization. This is natural inclusion. Oh, not inclusion, this is natural map. And the kernel of this map, what the kernel? This is such elements which goes to commutator of G. So its kernel is intersection H with commutator G modulo GH. And this is second homology. And again, this is kind of Hopf theorem for Lie algebras. Second homology is just have this description in the terms of free resolution of your Lie algebra. But here we need to understand what this action. That this action is exactly this commutator adjoint action, and we will see this from standard resolution as for groups. And the last time, and the last thing which was considered is the following thing. Again, if you consider two G modules, then we can define the tensor product over K just as vector spaces. And we have G module structure here. G module structure. It's just acts as usual. If M is right G module and N is left G module, then this is the section. One can check that this is left G action. On tensor product, this exercise is left G module structure. Coinvariance of this action is just tensor product over G. And the same story for home. The same story for home. If we have two left modules or right modules, here it was right, was left. Now, if they're both left or right, left for example, then we can consider their home between them over K, just as vector spaces. And again, we have left G action by the following rule. Phi acts on M, it's just by this rule. Again, it's an exercise to check that this is a left G module structure, and invariance now it's G module maps, G module home by definition. Okay, and now as for groups, As for groups, one can consider the following spectral sequence. Yes, and and again we have lemma that the diagonal action with UG itself is just, it's an exercise to check that for any module this diagonal action is isomorphic to the action from the right of UG from the right. It's the same as for groups, it's isomorphic. But it's not very important. The important thing is that we can consider K and free UG resolution. Free UG resolution. And some module M. And also some free UG resolution. We can consider the following cochain B complex. Just as I did for groups over G of tensor product over K with this diagonal action to N, to some another G module N. And then from this B complex we can obtain two spectral sequences, and the one spectral sequence gives us from this B complex, as for groups, I did this on the previous lecture for groups, we obtain spectral sequence of the following form: X P G from K, X Q over K M N converges to X P plus Q G M N. Again, this works for any commutative ring K. This spectral sequence exists. But in our situation, we consider only when K is filled, or at least when our models are free over K. For example, our case of consideration, of course, when K is a field. And then this general spectral sequence degenerates drastically, because in this situation, when K is filled, we have no X. We have only X0 is home. And so in our spectral sequence, we have only one column. So this 1, 0 column coincides with the infinite page, with the target. And so from this, we obtain the following observation. It's a very important observation. That over field, as for groups, over field, it's also true. But for the algebras, it's also important that the right side, we obtain X P between two G modules over G. And this is isomorphic to XP with K with coefficient in home. X from K to some G module, where here we consider G module structure on home. It's the same thing as homology. So we obtain this isomorphic to homology with coefficient in this home module. It's important observation. We will use it at the moment. For example, X1, from general perspective, it's X1 classifies extensions of G modules. For example, X1, Mn, the same thing as extensions of this form of G modules. And now we know that this is the same thing as the first cohomology of G with coefficients in home from M to N. So in fact, these extensions are classified by cohomology with coefficients in some home module. Okay, this is what we have done the last time. Now something new. Something new is the standard resolution for the algebras, which will allow us to explicitly calculate, for example, those actions of quotient on abilization of a subalgebra. Standard resolution. Standard resolution. It's so-called Chevalley-Eulenberg resolution. Eulenberg, no, or just Kazul resolution, because it's in fact it's just generalization of the Kazul resolution. If we have G is abelian, if G is abelian Lie algebra, then universal enveloping algebra is just algebra of polynomials of a basis of G. And we have already considered Kazul solutions for models over polynomials. And now this is just generalization to non-abelian Lie algebras. No definition. Consider the following tensor product. No, as for Kazul resolution. For Kazul resolution, we considered polynomials tensor with lambda of the same set of generators, let's say alpha, with some Kazul differential. Kazul differential just sends, no, we have maybe x alpha. Sends just x alpha to E alpha, and then we used Leibniz rule for the differential. Now here also we have the G, but differential also differential here is the sum of two parts. One part of the just Kazul resolution, just Kazul differential, and the another part, it's some additional part, comes from multiplication, no, commutator in G, which is 0 here. So, let me fix my notations, maybe. No, okay, yes, okay. Differential. I have some element U from universal enveloping algebra tensor with some exterior product of some elements of G. X1, xk. Xi is just vectors from G. This is some exterior product. Now, of course, by linearity, it's enough to define differential of these things. And this is two parts. One part is just Kazul differential. Kazul differentials, what does it mean? It means that I have each factor here, and differential on it is just xi considered as an element of universal enveloping algebra, and I have multiplication of this element here. No, this is this thing. Just Kazul sign, number of transpositions here from 1 to k. And then I consider this element now as an element of universal enveloping algebra and consider this multiplication. Tensor with this exterior product without this factor. And we have another part where sum is over all pairs where I is smaller than j. This is sign. And now it just comes from commutator in G. I have this commutator on the first place. No, and then I have these two places. So here the length of this exterior product decreased by 1, and here it's decreased by 1 also, because I have two replaces elements, but I have one new element. Okay. So now from this formula, now it's explicit calculation. For bar resolution, it was some cheating calculations with free products of associative algebras. here I don't know, cheating calculations here. No, it's just explicit exercise. Explicit exercise to check that this differential is correct differential, and this is squared 0. It's important exercise. But from this formula, for example, if we checked or believed that this d squared 0, then we obtain resolution. We obtain that this differential is, from formula it's clear that it's UG module map, it's UG linear, because this UG quotient, UG factors remain from the left, unchangeable. And it decreases exterior degree by 1. So if we consider this graded algebra, exterior algebra as graded algebra, we obtain the following situation. We have K, we have UG, this is UG, tensor K is the 0 part of exterior algebra. This is our argumentation, and then we have now starts of our, this is G, this is lambda 1. It's 1 degree part of exterior algebra. It's already this Chevalley-Eulenberg differential. Now then UG tensor lambda squared, and so on. We obtain this is chain complex. Chain complex of UG modules. All these UG modules are free. Because we are overfilled, then all these K vector spaces are free, and we consider UG module structure from the left, so this is just free UG module. This is UG tensor over K by some free K vector space. So this is a chain complex of free UG modules. It's important thing that it's finite, it's always finite. If G is finite dimensional, if dimension of G is finite, for example, freely algebras, they are not finitely dimensional in general. If it's but for finitely dimensional algebras, we obtain that this chain complex is finite. It ends by lambda dimension G, and it will be 0. So if we at the moment prove that this is resolution, this exact chain complex, then this is free resolution of K, and so from this will be the corollary. So okay, theorem that this is this chain complex is exact. So it's free resolution. It's called Chevalley-Eulenberg resolution, or standard resolution of K over UG. It's free. It's chain complex. Now we only need to check that this is in fact exact. So kernel coincides with image of differential. And so if we will prove this, then we obtain that for finitely dimensional with corollary, easy corollary, that homology and homology greater than dimension of G in any module, of course, are 0. For groups, it's similar to the, for such groups for which we have finitely dimensional classifying space BG. Of course, homologies are bounded above from the dimension of this BG. But for example, for finite groups, they're infinitely dimensional in general. For some groups, they're finitely dimensional. But for example, if G has torsion, then in fact it must be infinite dimensional. So it's a little bit more rare situation than for Lie algebras. For Lie algebras, of course, our usual situation is that our Lie algebras are finitely dimensional. So in the algebras situation, we have finitely the boundary on dimension on homology in general. It's much more usual than for groups. For groups, it's a little bit special property of a group. Okay, now we need to check this, that this is exact. And we will use this resolution because for example, in some low dimension, these differentials are kind of, no, they're very explicit and they're not very hard in low dimension. Consider again our Chevalley-Eulenberg, maybe chain, I think it's chain complex. With our differential. Consider filtration. We will use the special sequence argument. Consider the following in decreasing filtration. It's chain complex, so increasing filtration. Elements of P filtration is just vector space generated by the following elements. We have some monomial. We fix some basis. E alpha is basis in G. Fix some basis. This is monomial in this basis. This is this is ordered monomial. So ordered monomial. So this is part of the basis of universal enveloped algebra by Poincare-Bergouin theorem, and tensor with E G1 to the E J N. Here it's M. M is cardinality of I. So here it's also ordered, and this is also the part of basis of extrareal algebra. And P, no, is just that the common weight of these two monomials are not greater than P. So length of this word and length of this word not greater than P commonly in sum. And this is vector space generated by such monomials. Of course, it's increasing filtration, and of course, this is we have 0, F0. So this is in fact K. It's generated by words of length 1. It's just vector space generated by unit. F1, F2. Of course, in general, it's infinite, because in universal enveloped algebra we have arbitrarily large monomials. But it's increasing filtration, and of course, union of all elements. Of course, it's all our Eilenberg-Chevalley complex, because of course any element have some length. Any elements is sum of the finite number of such things, and we have maximal length of these things. Of course, okay. So we can construct spectral sequence from this filtration, from this complex. We just consider the central spectral sequence from filtered complex. Yes, maybe, okay, no, let's start. By definition, we obtain, okay, what the E0? E0 is just quotients. It's homological spectral sequence. E0 is just Fp of Cp plus C E P plus Q modulo Fp minus 1 Ce P plus Q. And this is the start of the spectral sequence, and then it converged to H P plus Q of Ck. We need to check that this is 0. That all homologies of our chain complex are 0. Using this spectral sequence, our claim that this is 0 if P plus Q more than 0. In 0 dimension, it's K itself, because it's a resolution of K. Yes. Okay, this is our claim. In fact, we see that no, because here P plus Q is P plus Q. P here is the common length. P plus Q its length of exterior part. So in fact, we obtain that this inequality means that p plus q plus n plus something, it's not greater than p. This means that, and n is also non-negative. So this means that q, of course, not greater than 1. So in fact, this spectral sequence of the second quadrant, we have p, q, and we have this part. We in the area p plus q not greater, not less than 0, because p plus q is just exterior length. P and p not greater than 0 because p is the common length. But no, this means that q not positive. We in this area. P not greater than not less than 1 and p plus q not less than 1. So this means that q less than 0. Okay. Let's go homological specification. So we have seen that in fact it's not very obvious that this spectral sequence stabilizes, because we maybe have infinite many differentials. But we have seen now at the moment that in fact it's stabilized on the first page. On the first page. And so it really converges and gives us what we want. Okay, now let's see. Our main claim that we have 0 page. On 0 page, we have 0 differential. 0 differential is vertical differential below in degree, degrees in degree. It's vertically below in differential. No, and our claim that these columns of the 0 page, sorry, they're on the second quadrant. Okay. Our claim that these columns is 0 with 0 differential. All these columns are exact, except of this 0, 1, where I have k without differentials. Okay, it's not exact, but all other columns are exact. What our q, if q more than 0, then this column for any q is exact. If we check this, we obtain that all columns are exact. So the first page, the next page, is just 0 page, except of this k in 0 differential, in 0 degree, and then I have zeros. No, then if I have spectral sequence with some exhaustive filtration, with some filtration which is the union of my whole chain complex and bounded below, and in this spectral sequence of this filtration I have that some page is 0, of course my homologies are 0. Why? No, maybe, okay, let me check this exactness, and then I will explain why it implies that my homology of chain complex is also 0. Why this is 0? Because these columns are just causal resolutions over polynomials. What the quotient? Consider the following thing. Consider, for example, degree 0. It's when we have no exterior part, and consider fq. I have only q monomial part and 0 exterior part, and quotient by this thing, denoted by aq. No, it's just k vector space generated by monomials with I of cardinality q in G. Ordered monomials. And by definition, in general, PQ is FP P plus Q quad by FP minus 1 CP plus Q. We have P plus Q exterior part, P plus Q degree, and this quotient. So in fact, no, yes, we have this thing A minus Q. Q must be non-positive. Then there is lambda P plus Q of G. This is by definition. I have quads only by length of word of my CE. Not length of word of exterior part is the same thing. So it's just tensor, and this is our quotient. And our differential, what the our differential on this quotient? No, our differential has two parts. You have the first part, it's Kasul part. And not Kasul part. And not Kasul part. But, okay, and let's consider induced differential on these quotients. But in these quotients, what in these quotients? No, what the induced differential? Induced differential is the following thing. I consider some elements from here. It's some element of quotient. I consider any representative, some elements represented by this thing. Then apply differential, and then quotes by F, where my differential goes. My differential, where my differential goes. Yes, in general, my differential acts something like this. PQ goes to E0, PQ minus 1. So it must goes to A tensor P Q minus 1 minus Q plus 1. So it's the F P, CE P plus Q minus 1 modulo F P minus 1 CE P plus Q minus 1. Вот, and okay, it's just, yes, consider not in this form, but it's just F Q minus 1 CE modulo F Q minus 2. Yes. No. Minus Q plus 1 F minus Q. Во. CE. Tensor is L P plus Q minus 1 lambda. So what I want to say in this quotient, no, maybe okay, it can be understand from some other directions, some different sides. No, just what I just to say is that the second part is 0 in this quotient. This quotient of filtrations. No, for example, No, yes, no, because no, maybe it's obvious without these considerations. Because the second part of my differential, no, increase my filtration number, because my filtration number on FP is the sum of two lengths, of UG length and exterior length. But my second part, it decreases exterior length by 1 and does not change this universal enveloping algebra length. So the common length decreases by 1. So if I consider on my quotients by the previous degree, if I consider element of filtration FP, then my differential sends it to some first part. First part does not change filtration degree because it decreases exterior part length by 1, but increase this length by 1 also. So this common degree does not change. This filtration degree does not change from FP. And second summand is just from FP minus 1. It's increased degree. So on my quotient, it will know this part. So on my quotient, I just obtain the first part differential, its identity, and this first part. But this first part is just, by definition, Kazul resolution. Because, yes, maybe in what set is Kazul? Minus 1 plus 1. In the following sense, if we consider what is AQ? A is star. It's direct sum of AQ. No, it's just, no, by definition, it's just associated graded quotients of your enveloping algebra. Your enveloping algebra is filtered algebra, and their associated graded quotient is just A. It's like algebra A. It's associated graded quotient of your enveloping algebra. And from Poincaré-Bergov-Witt theorem, we have discussed also the previous time that because of these monomials are basis of universal enveloping algebra, on quotient, you obtain that the same monomials are the basis, but now they are commute. So we obtain that this thing is just polynomial algebra on the alpha. So we obtain that each column is just polynomial algebra with Kazul resolution. And now this is just Kazul resolution. We have polynomial algebra, tensor product with exterior algebra, and formula for differential, which sends, no, if we apply this first part differential for xi, we obtain that this is xi considered as an element of polynomial algebra. So it's just Kazul resolution by definition. So we obtain that each column in our spectral sequence just coincide with Kazul resolution for this polynomial algebra. And so this is exact, because we know that Kazul resolution is exact. And we see that this works over any ring, commutative ring, if your Lie algebra is free module. Because Poincaré-Bergov-Witt theorem is true for Lie algebras which are free modules over commutative rings, and Kazul resolution is also true for any commutative ring. So in fact, if you have Lie ring, it's Lie algebra over Z, and if this is free abelian group, this is also true, of course. You have standard resolution. And this will be also free, because okay, so our claim is true. Each column is just Kazul resolution, and so it's exact. And so why it's enough for us? No, because it's general fact. If we have chain complex, and we have filtration, increasing filtration, which is exhausted, means that the union of all elements of this filtration is C itself and bounded below. So for example, we obtain that f minus 1 is 0. And then we can construct spectral sequence from this filtration. And then spectral sequence really converge to homologies. No, I just say about this because formally speaking, in our considerations before, for simplicity, I considered filtrations which are locally finite, which means that in each degree of this complex, filtration will be finite. It's not this situation. But in fact, this exhaustedness and boundedness below, it's also enough for convergence. But okay, no, it's kind of exercise. What I mean convergence? No, it means that we have some filtration also exhausted on homologies, and all quotients are infinity page. So we can define infinity. But what is infinity in this situation? We need that infinity will be defined. So if our spectral sequence stabilizes, which means that for any PQ there exists some n such that all differentials inward and outward are zeros for all, yes, started from some page. So in fact we have some number such that it can be defined by infinity. If this situation holds, maybe it doesn't hold, for example. But if it holds, then we obtain that we have infinity page, and then the exercise that in fact in this situation, of course, we also have filtration on homology of C itself, and quotients of this thing is this infinity page. So we need two things. We need that our infinity page correctly defined. So we need some number in each PQ such that infinity page defined. And also we need that if infinity page defined, that we have some filtration on homology such that this thing is true. Now what I claim that if infinity page is defined, that this property of filtration is enough to this property. Why? No, maybe it's in general it's an exercise, but in our situation we obtain. No, maybe we obtain that in our situation, our infinity page. No, in our situation is just the first page. It's just zeros, and I claim that then homologies are zero of C itself. No, this is very easy. So let me check this. No, okay. Consider some cycle from C. Some cycle. By definition, we need to just remember the construction of spectral sequence. From construction of spectral sequence, we have RPQ, we have R cycles, and R boundaries. And here, not just exactly this, but it's pi of them, where pi is projection. Pi is projection from Fp, Cp plus Q to Fp modulo Fp minus 1, Cp plus Q. It's projection on the quotients. So this is submodules of quotients. Okay, this is DC. Because of my filtration is exhausted, there exists some P where my C lies. So C is in some Fp. Okay. Now, for this, and it has some degree. So in fact, it's some P, Cp plus Q. We have some P and some Q. For this P and Q, there exists some large n. In our situation, is 1, but okay, this is not important. Now I prove this thing, if E infinity. For this PQ, there exists some large n such that this is 0, maybe. What does it mean? My C, because of DC is 0, of course, it's just a real cycle. So of course, it's R cycle. So of course, C lies in ZRPQ. Because ZRPQ is by definition elements from Fp, Cp plus Q, such that differential of them lies in Fp plus R. P minus R. Okay, that's increasing. P minus R. No, because our C is a real cycle, of course it's R cycle. Okay. So we obtain that it's 0. So pi of my C is pi of some BR, of element from BR, but BR is some R boundaries, but in particular is boundaries. It's in fact boundaries. It's D of C, P plus Q plus 1. So in fact, this is D of something. What does it mean? This means that C minus dy in kernel of pi, and this means that modulo some boundary, I obtain element from the previous filtration, And now I again do the same thing, because this is now a cycle from the previous filtration, and now from P minus 1 and Q something, I obtain another large n such that it's 0, and obtain another element, modulo which I obtain element of the previous filtration, and so on, so on, so on. And this is another part where it's important that my filtration is bounded below, because from the finite number of the steps, I obtain that modulo some elements, maybe P, I obtain element from F minus 1, which is 0. No, so my C is sum of boundaries, so it's a boundary. So my cycle is boundary, and I obtain that all my homologies of C are trivial. Okay, so yes, we obtain that homologies of my Chevalley-Eulenberg complex are trivial because I have spectral sequence converged to them, which has 0 first page. And this first page is 0 because all columns of 0 first page, and this first page is 0 because all columns of 0 page are Casull resolutions. Okay. Now consequences, corollaries. Now consider, yes. So I can use this standard resolution to calculate homologies and homologies. For example, for example, if I want to compute homologies, now I need to consider this Chevalley-Eulenberg. That I have M tensor over G of this Chevalley-Eulenberg complex. But of course, this is free resolution. So in fact, this thing is just this tensor over K over this thing. And homology of this chain complex is just homology of G with coefficients in M. And what the differential? Differential acts by the same formula. By the same formula. I have Casull part and not Casull part. By the same formula. And similarly for cohomology. Cohomology is computed by Hom over G from free modules to M. And because it's free modules, I can eliminate UG and just obtain modules over K from this cochain complex to M with the similar codifferential. For example, let's check again that first homology. What the low dimensional homology and homology. The first one, for example, what if M? Okay, any M. I have I have M, then M G. Then M lambda 2G. The 0 part, first, second. What's the differential here? Here, differential M tensor X goes to, here is just only Casull part, because not Casull part is 0, it's Mx. And so quotient is by definition coinvariance, it's 0 homology, it's true. Now first homologies. I have M tensor XY. Now it has two parts. It goes to mx tensor y minus my tensor x, and plus, but here 1 plus 2. It's 3, so it's minus m tensor commutator. So let m is trivial. If m is trivial, then this map is 0, so all kernel is this is itself. And if m is trivial, we obtain that first homology with m tensor G modulo this is m tensor m, no, and again m tensor x is 0, m tensor y is 0 if m is trivial. So we obtain just m tensor all commutators. No, this is just m tensor abelianization. So we obtain that first homology is abelianization. If m is trivial. If m is not trivial, we have some another things. Okay. Now what about cohomology? About cohomology. What the second cohomology, for example? No, again, maybe okay for cohomology. For cohomology, we have yes, I have hom from k to m. It's m. Then hom from g to m. Hom from lambda squared to m. Hom lambda third to m, etc. It's my Chevalley-Eulenberg cochain complex. Let me note that hom from lambda k gm, it's skew-symmetric forms, skew-symmetric maps. It's skew symmetric k polynomial, okay, multinomial, yes, multinomial forms from G to with values in M as vector spaces. So what's the differentials? Now here it just constants, forms in 0 variables. It goes to form which sends x to mx. It's just if for example let m is left model, then xm. Okay, just constant form. Okay, now if I have some form delta phi in 2 variables xy is phi x phi y minus y phi x minus phi of commutator. It's skew-symmetric. And this thing goes to 0. No, and finally, what the two cocycles it's phi into variables such that their differentials in 3 variables is 0. No, I will not write down explicit formula. It's by the following rule. I have it's kind of maybe it's kind of x y z. I have x phi y z minus y phi x z plus z phi x y minus phi commutator x y z plus phi x z y minus phi x y z x, something like this. And this will be mass 0. It's cocycles modulo such things. It's second homology. And again, as for groups, we have that from this explicit description, we can relatively easy check the following theorem. That the second homology in bijection with extensions of the form M, E, G, where E is Lie algebra, it's extension of Lie algebras, where M is considered as abelian Lie algebra, so with no commutator. But M is G modulo, and if we have any such extension, then quotient acts on kernel by commutator. But this action x from G, M from M is correctly defined, and we consider exactly this action if the action on M is fixed in this situation. So for fixed G action, we consider the set of all such extensions where action is fixed, and M is considered as an abelian Lie algebra, and the set of such extensions is in the bijection with second homology. No, this is the same thing. We consider, it's an exercise of course, but steps are similar to group situation. We consider any k-linear section. If we have k-linear section, we obtain skew-symmetric bilinear form. xy is just x sy, commutator in E minus xy. One can check that this is cocycle, two cocycle. One can check that if I consider another section, then two such sections are differed by some beta, and then cocycle differs by differential of this beta, or more or less maybe minus beta, something like this. So this class, so we have correctly defined map from the left to the right, from the right to the left. This map is surjective, so because for any extension E, for any cocycle phi, I can define extension. No, it's just direct sum. Yes, with the following commutator M, G, it's E phi, M prime, G prime. No, it's just M. No, if it's left model, then G M prime minus G prime M plus phi G prime G prime. One can check that this is Lie algebra, and this is an extension of G with M with this G action here, and I have a canonical section which sends G to 0G. This is not Lie algebra section, but it is k-linear section. So, and you can check that phi s is exactly phi. So this is surjection. No, and again the same argument proves that this in fact is injection. So this is bijection with the same formulas. And finally, now if we consider short-rank sequence of Lie algebras, short-rank sequence of Lie algebras again for Hopf's theorem. I need to understand what the action of quotient on homologies, on abelianization, for example, on each homologies, the first homology of H with coefficient in K. How it works in general. No, it's the same as for group situation. It's exactly the same for group situation. Let me recall. It follows from the following thing that that Tor Yes, Tor 1, what with the first homology, jk is Tor over j from k to k. And this is isomorphic to Tor over g between ugh to k. And on this we, of course, have action of g quotient, it's action of, the same thing. It's action of the universal invariable algebra of quotient here. We have this action, and action here is through this isomorphism. And so why this isomorphism is true? No, this is as for groups. We have, again, consider free resolution of k over g. And now just notice that if it's free resolution over g, then it's free resolution over h also, because ug is also free UH model, as we said before. This is also it's free G resolution. So this is free H resolution, because UG is UH free. UH free. And so if I tensor it over H with K, I obtain what I obtain? No, I obtain, what? Here's H. That's homology of H, sorry, it's stabilization of H. Yes, sorry. Stabilization of H, what? On the then if I obtain some chain complex and its homologies, it's from on the one hand it's just Tor between k and k, it's just homology of H, so it's just homology of H with coefficient k. But on the other hand, it's just will be the following chain complex, because UG tensor. No, let's consider standard complex, of course. Tensor lambda G, and then tensor K over H with UG is just UG what's by H. So it will be, I obtain something like this. And this is a chain complex of modules of this ring. So we obtain ring module, the module structure over this invariant algebra on this homologies, because this homologies is homologies of this chain complex, and this chain complex of UGH modules. So this is our action. We obtain this action of this algebra on these homologies, and this is now easy exercise. If you consider exactly this standard resolution for this module and consider first homologies on this thing, tensor J. Consider first homologies and consider the following, the corresponding action. You obtain that this is action GH on first homology, so on abelianization is just by this commutator. It follows. It's the same manner as for groups, but even easier. It's even easier because it's a linearized situation. It's from standard resolutions more or less immediately follows that from these formulas you obtain that this is exactly this commutator action. And so we obtain Hopf theorem, because we now understand this action from standard resolution, for example, and obtain Hopf theorem. Okay. Now I want to discuss some homological aspects of theory of semisimple algebras and their representations. It's some kind of easy applications of homologies. Easy, but not trivial. Before this, some topological interpretation. But let me have G is a Lie group. Lie group. Then there now we over field of real numbers. Then their tangent space in the unit is Lie algebra. It's a corresponding Lie algebra. For any Lie algebra, there exists Lie group such that it's the tangent space over real numbers. But now I want to consider the situation. For any G, there exists such Lie group. Such Lie group is not unique, but if you consider simply connected Lie group, then this Lie group is even unique, for example. And then the first claim is that cohomology of G as Lie algebra is isomorphic to invariant de Rham homology of G. What the invariant de Rham homology? No, we can consider G is a smooth manifold, so it has de Rham homology, has de Rham cochain complex, de Rham. It's cochain complex of differential forms, and differential form, no, we have action of G on itself. For any G of G, we have action of by left multiplication, for example. By left multiplication. Now the form, it's subcomplex of invariant forms, is just such forms which are invariant. So if we have pullback of omega, it's just omega. It's subcomplex. And this subcomplex, in fact, isomorphic to Chevalley-Eulenberg complex. Chevalley-Eulenberg complex of G. Yes. Just no. Что-то не так. No, sorry. Not exactly this, sorry. But it's obvious that any invariant form uniquely defined by its its form. It's just skew symmetric. For example, K linear form on tangent space in each point. But because of this invariancy, for any point G in G, we have translate this point to the unit by multiplication by G inverse from the left. And by invariancy of the form, this form is just determined by its value in the unit. Value in the unit, it's just K linear form on the tangent space of unit. It's just K linear form, just home. K linear form, yes, вот так вот. K linear form on unit. It's just L lambda K G. Yes, and from this identification, one can check that the Rham of invariance form, cochain complex, from this identification, if it's evaluated in unit, is just isomorphic to home from Chevalley-Eulenberg complex to R. No, it's just what lambda G to R. You only need to check that usual de Rham differential coincides with this differential. No, it's known formula from differential geometry that if you want to compute differential on some vector spaces, vector fields, then you have exactly the previous formula. You have this part where you have xe differential of your algebra of your form, and then without this thing. this form and this differential of this function, and plus minus 1 e plus g form of the commutator and all other vector fields. And you can check that if you evaluate this in the unit, you obtain exactly Chevalley-Eulenberg. So from this point of view, Chevalley-Eulenberg is just invariant theorem complex of Lie group, of any Lie group. Okay, and now let's me assume that our group G is compact. Our group G is compact. No, and connected. Connectedness, I of course will assume because if it's not connected, I only see about the algebra, so I only consider the components of the unit. So I can assume that it's connected. It's compact. Not for any Lie algebra there exists compact group. Compact group with the fixed, no, with our Lie algebra as the unit tangent space exists if and only if there exists invariant scalar space, invariant scalar space, как это называется? Invariant scalar product, yes. Invariant Euclidean, invariant symmetric, positively defined bilinear form on G. Invariant means that it satisfies something like this. It means that it's invariant, and if such if and only if, then there exists a compact Lie group with our unit tangent space. No, so it's not always exists. But okay, now let me assume that it exists, and if it exists, then for compact Lie group, in fact, invariant chain complex, quasi-isomorphic. No, we have quasi-isomorphism. Our inclusion to general theorem chain complex is quasi-isomorphism. It has quasi-isomorphic in fact it has quasi-isomorphic inverse. I have inverse map. It's also quasi-isomorphic. No, this map is just inclusion. What the inverse map? Inverse map is just integration. If I have any differential form, then I consider translations by group itself of my form. Its form depends on G. I have integrate by G over G, and then divided by the integral of unit of G, the volume of G itself. This is har mir. It's the uniquely defined translation invariant measure on my Lie group. It exists. I can integrate on group. To guarantee that my integrals are finite, that means my group is compact. This is my compact. It's finite. It's compact. I can integrate by the whole G because G is compact. If G is not compact, for example, over R, I not always can integrate any one form. Over compact G, I always can integrate, and if I integrate this thing, it's again form. It's new form. Because here I have to calculate on vector fields, I just calculate on the integral. And this form is obviously invariant because I consider average of my form over my group. Okay, and this is my what? W to W tilde. It's my map in the other direction. Obviously, it's cochain map because differential does not depend on this integration. because differential is just about evaluation of my form on vector fields, and it does not depend on integration over translations. So it's cochain map. And why it's quasi-isomorphic? No, because if I have invariance map include to any map and then average again, I obtain the same map. Because if my form is invariance, that is just omega integral by omega. It's just omega integral of unit, and this is g, and I obtain omega again. So this composition, of course, identity. What is this composition? This composition is if I have some form, and then it goes to invariant form. I claim that they have the same homology class. So I mean that its difference is just co-boundary of something. Why? Because what is omega tilde minus omega? I know this is important why G is connected. Because G is connected, for any element G of G, I have a path from G to unit. From G to unit. This means that multiplication by G on G to itself is gamotopic to identity. This means that by homotopy invariance of the RAM forms of the RAM cohomology, this means that pullback of omega is cohomologous to omega. So minus omega, it will be differential of some codifferential of some form depends on G. So the thing is just what is this? Is 1 divided by volume of G, integral over G, pullback G minus omega. Now here I can use that omega is itself integral over unit divided by G. This is just G, and it is the same thing. And this is differential of theta G. And now I obtain. Now again I can move differential under integral to the out integral, and I obtain that this is differential of this average theta G. This is some form. This is d theta. So difference is the d theta. Here, you need some arguments why this thing is integrable, because in general this is not continuously depends on G, because this path this path does not uniquely this path maybe does not continuously depend on G, but maybe you can consider but you can check that in fact this form is integrable, and this is correctly defined differential form. It's smooth on these variables. It's only need to be integrable. It's integrable. Okay, so we obtain that it's the same class, and so this is quasi-isomorphism. So we obtain that for G is compact and connected, then cohomology, the RAM homology of G is just isomorphic to cohomology of tangentially algebra with coefficient in R. For not compact is not true. For example, first cohomology of R as Lie group with coefficient in R as trivial module. It's just stabilization of R. It's just R itself. But the RAM cohomology, of course, of R is 0. This is invariance cohomology again of R. And it's not 0 because, for example, dt is invariant one form on R, but of course it's codifferential of something in the whole the RAM complex, but it's not differential of any invariance function, because invariant function is just constant functions. So this is co-boundary in omega itself, so the RAM homology is 0, but its generator of the first invariance homology is not co-boundary in invariant the RAM complex. So invariant the RAM homology is just R generated by dt, and it coincides with the Lie algebra, but that does not coincide with the RAM homology in general. Okay, now it was about Lie groups, and now about Lie algebras. Semi-simple Lie algebras. about semisimple Lie algebras. First of all, okay, let's K is, of course, it's field. G is finitely dimensional Lie algebra over K. K will be of characteristic 0. It will be important. Now, okay, what is semisimple Lie algebra? What is simple Lie algebra? Simple Lie algebra means that this means that G has no non-trivial ideals. Has no non-trivial Lie ideals and not abelian. So one-dimensional abelian Lie algebra is not simple. Okay. Lie algebra is semi-simple. Means it has no abelian ideals. We have no ideal abelian ideals. No, not zero, of course. Only abelian ideal is zero ideal. It's the same thing that has no non-zero solvable ideals. Maybe let me recall what solvable Lie algebra. For any Lie algebra, I can consider its commutator. Then I can consider commutator with commutator. Just commutator of the previous one. It's not nilpotent, and so on. It's commutator of this thing and so on. And if this filtration is ends by 0, if it's finite, then we say that G is solvable. Solvable Lie algebra. For example, abelian groups, it's just solvable of the length 1. For example, if you consider algebra of matrices is associative algebra, in any associative algebra you can consider associative commutator, and it will be Lie algebra now. So matrix algebra with this Lie commutator, if you consider subalgebra of upper diagonal matrices, it will be also solvable. No, of course, in Lie algebra theory you have some classification theorem that in some assumption any Lie algebra can be embedded as this upper triangular subalgebra in some matrix algebra. It's Lie algebra theory. It's not our case. Okay. And this is the same thing as has no non-zero solvable ideals. Why is the equivalent state? Because, of course, abelian ideal is solvable ideal. If I have non-zero solvable ideal, then I can consider commutator of the solvable ideal. And then I can consider this commutator series of solvable ideal. And you can check that all these things will be also ideals. And the last part will be abelian, because its commutator is 0, and it will be abelian ideal in the envelope algebra, Lie algebra. Yes, you can say that you can check that all the things are ideals. So it's the same thing. Okay. Now, theorem of Cartan. Cartan theorem. It's part of Lie algebra theory. It's a criterion for semi-simplicity of Lie algebra. G is semi-simple if and only if it's killing form, it's non-degenerate. What's killing form? I can consider my Lie algebra. It acts on itself by commutator. This operator, action by x, it's linear operator on G itself. It's defined by add x. It's linear operator, G to G, sends y to commutator xy. And so I can define this such bilinear form. Killing form xy is just, I can consider one operator, another operator is composition of two operators, this operator on G, and then obtain its trace. It's some number, it's some scalar. It's bilinear form. It's symmetric bilinear form. It can be degenerate or not degenerate. And so Cartan theorem says that this explicit form is not degenerate if and only if G is semisimple. Also, we have structure theorem. No, in fact, it's easier consequences of Cartan theorem, in fact. That J is semisimple, it will be denoted by this. If and only if G is just direct sum of finite number of simple Lie algebras. Simple Lie algebras. Of course, this decomposition is uniquely defined because this is just all simple ideals of my G. By simplicity, the commutator between others must be 0 because it's some ideal in Gi and in Gg, so it must be 0. No, maybe it's no, and because they does not intersect, because it's intersected by 0. But from simplicity, their commutator with itself must be also Gi itself, because it's yes. This is because this is ideal in Gj, and so they intersect by 0. It's of course 0. But here it's because simplicity, because it's some ideal in Gi, and so it's either 0 or Gi itself. It cannot be 0 because Gi is not abelian by definition. It's not abelian. So it must be Gi itself. And from these two things, we obtain that this is also true for semisimple algebras. For semisimple algebra, we have that commutator of G is G itself. So of course, it's kind of counterpart of solvable algebras, semisimple algebras. We will prove the Levy theorem that in fact any algebra is the semisimple, semi-direct product of solvable algebra and semisimple algebra. Of course, okay. Of course, yes, and of course it's not. Yes, it's exercise. It's no. This is it's proved by induction. If it's not simple, then it has some ideal. You have some direct sum, and using killing form, you can check that it's direct sum and so on. And doing this by induction. No, it's Lie theorem. Exercise that this structure theorem is not true in positive characteristic. That if you have positive characteristic, if you consider n is divisible by p, some natural number, then you can consider J of k is just all matrices n by n with commutator is just associative commutator. You can consider quotient by scalar matrices is center. It's called PJLN, or PJLN, yes, projective JLN. And you can check that this algebra is semi-simple It's semi-simple by definition. But no, it has two ideals. No, it's not direct sum of simples. In this situation, you can check. So it's just not true that in this formulation the structures remain positive characteristic. So for us it's important that characteristic is 0. No, for example, PGLN, commutator with PGLN is not PGLN itself. It will be PSLN. So this is not true. This is not true. Okay. Now about homology. What the first? What we already observed, that abelianization of G is 0 because commutator of G itself if G is semi-simple. So we obtain that first homology of G in K is 0. And first homology is just home from abelianization. K is 0 for G is semi-simple of a characteristic 0. Okay, now I need the construction of Casimir element. Let's consider some Lie algebra, semi-simple, and some representation of G algebra, so some G module. G module, yeah, is just representation of G. Finitely dimensional, of course. M is dimension of M. So we obtain the action. Action is some representation, as I said before, is a Lie algebra homomorphism from G to endomorphisms of M, which sends commutator to associative commutator. It's definition of G module. It's just J, M, K. It's matrices of M and M. Define the image of this homomorphism by H. It's some Lie subalgebra of JLM. H isomorphic to quotient by G by kernel of rho. Kernel of rho is ideal. From structure theorem, we obtain that in fact, for semi-simple algebras, any ideal is sum of these ideals. This is minimal ideals just. So any ideal is the direct sum of these ideals. So quotient by this is also its direct sum of the remaining ideals. So this is of course semi-simple. Now what I just said that any image of semi-simple is just semi-simple. Okay. It's also semi-simple Lie algebra. But now this is semi-simple subalgebra of matrices. Okay. Also Cartan theorem is in this situation that if we have G, in our situation H is semi-simple and subalgebra of some matrix algebra, then we can just define this bilinear form beta is just trace of multiplication of these two operators in matrices, and then consider not consider just a joint representation, but consider this given exact representation, consider this composition and consider trace. It will be also symmetric bilinear form, and if H is semi-simple, then beta is non-degenerate. So in our situation, this form is not degenerate on H. Also, you can check that beta is invariant in the previous sense. Invariant. In the moment I will say what the invariance also equivalently means. What does it mean? Yes, I can consider the following thing: endomorphism of a K of H. Consider H as just as a vector space, and this endomorphism consider as Okay, it's just vector space now. It's isomorphic to H tensor H dual. It's from linear algebra. And now this is isomorphic because through the non-degenerate symmetric bilinear form, we have isomorphism with H tensor H. We have isomorphism between dual H and H itself through beta. And now here I have inclusion to G tensor G, and I have inclusion to UG, to universal invariant algebra. No, maybe here it's not. Well, it's not inclusion, yes, it's not map. And now I have identity here. It goes to some element of universal invariant algebra. This element called Casimir element of the given module of a G. It's Casimir element of module M. By definition, this element lies in the image of the thing, so in particular it lies in augmented ideal. It's generated by G and G. It's not in unit. It has no unit, okay. It's by definition. The important thing that what we have here, as I said before, if we have G modules, we have G module structures on home between G modules and on tensor product of G modules. H itself is G module. Now because G acts on M, of course G acts on image of itself. It's G acts on H. H is G module. H is G module because action by commutator. Action by commutator, it's correctly defined because action by definition. It's commutator. It's kind of H is image of G in. No, yes, it's by commutator, but it's commutator in JLM. It's commutator in JLM. In JLM. So here it's okay. Gx from G and H from H. X H by definition is commutator of rho X and H in JLM. Then this will be a G module. So we have this also. G module is home between G module and G module with a natural G module structure. This from linear algebra isomorphism is always isomorphism of G modules. This G module structure coincide. If we consider N dual as home from N to K, where K we consider as trivial G module, this is also will be a G module, and this will be isomorphic G modules. This is always isomorphic G module. So this isomorphism is isomorphism of G modules. Now, invariance of bilinear form is equivalent to say that this induced by this bilinear form isomorphism is also G module isomorphism. It's also G module. No, in general it's H module, but G module structure is through H module structure. So bilinear form on G algebra is invariance if and only if the corresponding morphism is G module morphism. And now this is G module isomorphism. This is because of invariance. No, and now this is, of course, it's trivially seeing that it's always inclusion of G modules, and this map is also G module inclusion. So this morphism is G module morphism, is G module morphism. You need to check this isomorphism from beta invariance. Beta invariance is kind of something like this. You can easily check that in this situation, and you can check that from this, if you have this invariance, then this is the map of G modules. From this, we obtain the following. We obtain that for any x from G, if we consider this action x on identity in endomorphism module of H, This of course 0. Identity is from invariance of G action. So identity is from invariance of my module. Well, because by definition, my action is something like this. If phi is identity, I obtain xm minus xm. Of course, it's 0. So identity is invariance. Because my map is G modulo map, it sends invariance to invariance. So I obtain that Cm is invariance of enveloping G algebra. Now, what does it mean? That means that for any x in G, action of G module of G on UG is 0. Action by commutator, but action is by commutator in my sense. So x Cm is 0. It's action by commutator. Lie action. Okay, but okay, yes, in UG. But this commutator in my no, okay, and this means that no, sorry, this is not by commutator. It means that just action of G on UG, Lie action, is action by associative commutator. Yes, sorry, x u minus ux. Oh. So this commutator, this my G action is this is my G action on UG. Sorry, yes. This is not defined. Sorry, this thing is not defined. My commutator. What's commutator? This commutator, of course. So my identity is 0 goes to commutator in sense of associative algebras. No, this is then it's also 0. This means that my Casimir element commutes with any element x from G. No, because my associative algebra is generated by G, my Cm commutes with any elements, commutes with any element of my associative algebra UG. So the claim is that Cm is in center, is central element of my enveloping algebra. It commutes with any element. It's a result. It's from center and it's from augmented ideal. This is all what I want to know about it. Okay. We construct some central element, Casimir element of module. For any module, we construct some central element in enveloping algebra. Okay. Now, consider our module and extend our scalars. Extend our scalars by algebraic closure of our field. We obtain the module over algebraic closure of our field. The algebra over algebraic closure and so on. It's also G module. Now, Cm, it's some element of UG. My M is UG module. So my Cm is operator on this vector space of algebraic closure. Now we know Schur lemma. Schur lemma says that if I have Lie module over algebraic closure over algebraically closed field and some element x, if I action of UG, for example, okay, and some element x if some element x, yes, no, sorry, but if, one second, if M is simple, okay, let me say that M is simple. M is simple. It has no non-trivial submodules. It has no non-trivial submodels. Let me discuss this the next time. Now I just say that from Schur lemma, it follows the following thing. You can check the following thing. That in fact, it's an exercise for the next time. That my Cm, in fact, acts on M scalary by scalar. No, yes. It acts by scalar. Сейчас, так, нет, что-то мне тут не нравится. Okay, yes. Acts by multiplication by m dimension m divided by dimension h. No, dimension h divided by dimension m. If m is simple. If m is simple. So in fact, the also important property of this element that it acts by scalar of this form. If m is simple, it has no non-trivial submodels. The representation is irreducible. Okay, now I hope I will prove this next time. Okay, now we can obtain the following property, that if m is simple and G is semi-simple, then then simple and not trivial, with non-trivial action. Then all homologies and cohomologies of G in coefficient m are 0. All. So all homologies and cohomologies with coefficients in non-trivial simple modulus are 0 for semi-simple algebras. Now it's easy consequences of these facts on the board, because, for example, cohomology. Cohomology, it's x over UG between k and m. It's cohomology of Hom of some projective resolution to m, or cohomology of Hom of k to projective resolution of m. Now let me note that center of UG is some commutative algebra. It acts, if it's UG modules, of course, over not commutative ring, Hom over R is not R module, but it's always module over center. You always can multiply by central elements. In this manner, and because it's not R module, because R is not commutative, but if you consider some element which commutes with any elements in R, this is correctly defined also R linear map. It's also R linear map because R CF M is the same thing as C R Fm, no, it's just CFRM, so it's R linear. So we can multiply by central elements all these homes. All these homes are modules of a center. And so homology is also modulus of a center, and these model structures coincide, and we can compute this model structure from this home or from this home. It's the same home because we also can consider home from one resolution to another resolution, as we know. And this is also module of a center, and homology is also module of the center. So my central element acts on this cohomology. On the one side, it acts by multiplication in K. I can consider this multiplication in K and then consider this home. But because of Cm is from augmented ideal, it acts by 0 on K. So in fact, Cm acts by 0 on my homology because it's K here. But on the other hand, it acts on M by multiplication, because M is simple, by multiplication of this number. So we obtain that and it's because and here it's not 0. It's not 0 if dimension of H is not 0. H is image of my representation. Image is 0 means that my action is 0. It means that M is trivial. But we assume that M is not trivial, so my action is not trivial G on M. This means that H is the image of G in matrices on M. So H is not 0, so this number is not 0. So we obtain at the same time that my Casimir element acts by 0 and acts by non-zero element at the same time on the same module, or the same vector space. No, this means that this vector space is 0 itself. It's only happened when my vector space is 0. Here is important, of course, because that M is not trivial, because if M is trivial, then we know that first homology is abelianization, so it's not 0. No, sorry, we know that it's 0. Okay, yes. At the second, yes. In fact, no, yes, we know that only first and second, I don't know about higher. Okay. Okay, so we have, and also for homology, it's Tor, and it's also multiplication by non-zero number and from 0. So we obtain that is this theorem, that all homology simple modules are 0. So now we can obtain the following corollary. The following corollary. The Whitehead first theorem. No, Whitehead first theorem. The Whitehead first theorem that first cohomology in each module is 0 for any M if G is semi-simple. What does it mean? No, because if M is simple, then maybe if it's trivial, no, then we know it's home from abelianization is 0. Then it's 0. If it's not trivial, we just prove that it's also 0. If M is not simple, then it has some submodule non-trivial, and we have some non-trivial short-order sequence. With here is non-zero, here is non-zero, and this means that these modules has smaller dimension because we have finitely dimensional module. Of course, it's important that M is finitely dimensional. It's crucially. And so from long exact sequence, from induction by dimension, we can assume that from induction by dimension, we know that homology in this are 0, and then from long exact sequence, we obtain that homology of M is between 0, so it's also 0. Induction by dimension of our module. For one dimensional, it's always trivial, so it's also true. Okay, this is the end. Now, for example, yes, I didn't say that, but what is the first cohomology? First cohomology, it's so-called, no, what is one cocycles? One cocycles, it's such maps from G to M, linear maps, such that f x, y minus y phi x is phi of commutator. Yes, it's so-called derivations. Derivations of G with values in M, in G model M. And between all derivations, we have inner derivations. Inner derivations, it's co-boundaries of something. It's just derivations of the form x goes to xm for fixed m. It's inner derivations, and our theorem, Whitehead's first theorem, says that over semi-simple algebras, any derivation, any such function always has this form for some m. It's just differential of m, where m is zero cycle, zero cochain. Okay. Now we also can apply this to the following. It's Weyl theorem. It's a very important theorem. Weyl theorem. By theorem that for any, again, finitely dimensional module is completely reducible. This means that it is the direct sum of simple modules. Direct sum of simple submodules. No, it's also homological calculation. If M is not simple, if it's simple, it's reducible. If it's not simple, no, then again we have non-trivial short exact sequence of some submodules and some quotient module. But now we know that this extension is x1 M quotient L is isomorphic to first cohomology of G with coefficient in Hom from ML to L. But this is module of a semi-simple algebra, so it's 0. So we obtain that this extension is trivial, so it's direct sum. So M is direct sum is L and ML. And now we have induction on by dimension, and so on. So it's trivial consequences of the first Whitehead theorem, because we know that extensions classified by cohomology. And if we know that all first cohomology is 0, you can say that, no, it's just derivation. What? Derivation with coefficient in Hom is, for example, any extensions of any modules. So, yes, we obtain that it is Weyl theorem. Any finitely dimensional module over semi-simple algebra can be reduced in simple modules. G is semi-simple. It's very important, of course. No, and Whitehead's second theorem says that any second cohomology of semi-simple algebra is trivial also. Third cohomology is not always trivial, but the first and the second always trivial. Whitehead second theorem says that the second cohomology of G is 0 for any M, finitely dimensional, of course, and G is semi-simple. Now, why it's true? As we know, for Weyl theorem, any module is direct sum of simple modules. So, no, for direct sum of modules, cohomology is direct sum of cohomology. So, from Weyl theorem, it's enough to check without loss of generality. We can assume that M is simple. If M is simple and is not trivial, then we know that all cohomologies are trivial. So the only one non-trivial case is when M is trivial, in fact. So we need to check that second cohomology with trivial coefficients is 0. But we know what second cohomology is. Second cohomology classifies Lie algebras extensions, central extensions. So it classifies extensions of this form. extensions of the form. Here is Lie algebras extensions. Here is abelian Lie algebra and trivial G module. Because this module is G trivial, this means that K itself is central. So, no, central extension. So, in fact, K lies in center of K with any element of E is commutator is 0. No, it's exactly because of the action. Because our action of G on K is defined by choose any preimage and then acts. This is correctly defined action, and this action is 0. So we have that this multiplication is 0. Okay. Now, from this, we can define G action on E itself. Again, from consider any preimage of any element of G, we consider any preimage in E, which goes to X, and consider commutator. All these preimages are differed by elements of K, and because of K is central, this commutator does not depend on the choice of preimage. So this is correctly defined G action. This is G model structure on E. And we have that our projection pi is G module map because pi of this thing. Pi is Lie algebra map, so it's pi x pi E. So it's just x. This is by definition action of our x. This is x pi E. So this means that pi is G module map, where we consider a joint G module structure on this and this lifting G module structure on E. Pi is not just Lie algebras morphism. This is G module morphism. G module morphism is important. Okay, but now we know that. So we have G module exact sequence, short exact sequence. This is short exact sequence of G modules now. And then from Weyl theorem, we know that this G module short exact sequence is trivial, because from Weyl theorem we know that any, in fact, from Weyl theorem we in fact know that any short exact sequence of any modules of a semisimple Lie algebra is trivial as G modules, because it's also first homology with coefficient in home. So from this we obtain that in fact we have section which is G action, G module section. We have G module section. So we only need to check to obtain that this is trivial Lie algebra extension. We only need to check that this section is in fact Lie algebra section. No, this is true, because by definition S of commutator, because it's a G module section, G module, and this is action X on Y, it must be action of X on Sy, but Sy is element of E, and this action is the commutator with any preimage. But we can choose this preimage of this form. S of X is one of preimage, and this action does not depend on preimage, and so we obtain this formula. This is choice of preimage, Sx. No, this means that S is Lie algebra section, so we obtain that this extension is trivial from Lie algebraic point of view, and so because of this is true for any extension, we obtain that second homology is 0. So second Whitehead theorem is proved. Okay. Сейчас. Or maybe let me say the following thing. That let me say about Casimir elements. Maybe this is true that all what I said so far is true over algebraically closed fields, because if K is algebraically closed, if K is algebraically closed, then if M is simple, then, and if I have action of my algebra on M, and I have central element, any central element of my action. Now then, okay, consider my action C on M. It's some operator of M, because it's finitely dimensional vector space, and C is the operator, and we over algebraically closed field, then it has some eigenvalue. If we have some eigenvalue, and we have some eigenspace, we have some eigenvalue, and we have some eigenspace of my M, on which my C is scalar. But because my C commutes with any element of UG, this eigenspace is invariant. It's submodule. Because of this is submodule, G submodule of M. So, and because my M is simple, the submodule is even 0, but we know that it's not 0, it's eigenvalue, it's not 0 subspace. So it must be whole M. And we obtain that my central element is scalar. No, and then we only need to check that for Casimir element in this situation, that its trace is equal to dimension of H. Because then, no, from the, if we compute this, it's kind of exercise. No, it's because if I choose some basis of H, then by definition of my Casimir element, this Casimir element is just this. No, okay, it's kind of exercise. This I will say the next time, but now, no, and from another side, this is lambda identity, so it must be, trace must be dimension of M lambda. And so by divided, I obtain, as I said before, that Casimir is just dimension of H divided by dimension of M identities, scalar thing. And so all this theorem works over algebraically closed field. Maybe I did not know, maybe this is not true for not algebraically closed field, I don't know. But all corollaries, Whitehead 1, Whitehead 2, and Weyl theorem are true over not algebraically closed, because by trivial things, because these statements are not defined on, are not depend more or less on extension of scalars. Now, for example, what we have, first homology of G with coefficient in M. If we extend scalars with algebraic closure with the same action, we obtain this. This is just extension scalars of cohomology. And so if we know that this is 0, because this is for, we now know that for any module over algebraic closed field over a semi-simple algebra, this is 0. So we obtain this is 0, but it's just extension scalars. So if extension of scalars of vector space is 0, then vector space is itself 0. For Weyl theorem, the same thing. If I have some module, if my module of after extension of scalars is direct sum of some submodules, then before extension of scalars is also direct sum of no, but this is not true. But this is follows from the cohomology, because from this Weyl theorem follows formally, because it follows from first cohomology with coefficient in any home. In any home is 0, and then any extension is trivial, and then induction by dimension. So we obtain Weyl theorem from this, of course. And again, from this, again, the same thing. If my extension of scalars is just extension of scalars, if it's 0, so this is 0 over any field. So in fact, all this works over any field of characteristic 0, of course. The only exercise is to check that trace is equal to dimension of H, and it's from definition of Casimir element. So yes, this is sure lemma. It works over algebraic closure field, but for our corollaries about vanishing of some cohomologies, it's enough, of course, because extension of scalars does not very depend on cohomologies. If we obtain that it's 0, then it's 0 and without extension also. And well, theorem is corollary of this extension. Okay, that's all.